Okay, we're going to start looking at something called a system of equations in two variables, linear systems of equations in two variables. And what we need to figure out is what this means. We're going to look at types of systems and start with defining systems, what types there are, and seeing very quickly how they're solved graphically. So let's jump right in and look at some linear systems. Let's consider the equation x plus y equals 6. This is a linear equation in two unknowns, or with two variables. It's a straight line with variables x and y. We can graph that. And I want to leave some room. We could make a table, and if we graph it, if x is equal to 0, y is going to be equal to 6. So I've got a point here. And I also happen to have the point 4, 2. So let me write in these coordinates 0, 6. Got the point 4, 2. And if y was equal to 0, or were equal to 0, x would be 6. So I'm going to have the point, squeeze it here, 6, 0. 3 points, and they all fall in a straight line. That's very good. So I probably, when I calculated these, did them correctly. Don't have any points off in the hinterlands. Now, that's very nice. Nice little graph to go with that equation. I want to consider another equation at the same time. Let's consider x minus y equals 2. And I'm going to graph it on the same axes. So that's going to have the point if x is equal to 0, y is equal to negative 2. So I've got this, 0, negative 2. If y were equal to 0, x would be 2. So I've got this point here, 0, 2. Pardon me, 2, 0. Got to watch getting those x's and y's flipped. Let me zoom in a little bit. And if I were to put in a 4 for x, I would also come up with a 2 for y. And I'll draw a line here. You'll notice that both of these lines share the point 4, 2. The set of these two equations is called a system of two equations. And when I look at them both together and look at a graph, the place that they intersect is called the solution of the system. So let me just write that down. We're going to call this a set, or pardon me, a system. Name it a system of two equations in two variables or two unknowns. And the place that they intersect is the solution. What that means is the coordinates for this point satisfy both equations. If I plug those values in, I get a true statement. And we'll just test that. Let me zoom out again. If I put in to x plus y equals 6, the 4 and the 2, 4 plus 2, does it equal 6? Yes, life is good. And with the x minus y is 4 minus 2 equal to 2. Wonderful. Those coordinates make a true statement for each equation. That is, incidentally, the graphical solution of a system, the place where they intersect. Now, there are only 3 possibilities when you're working with systems. Of linear equations. It's 3 ways it can happen, and only 3. The first is like the one you just saw. You've got your x, and your y-axes, and you have a couple of lines, and they intersect somewhere. The place they intersect is the solution. This is called a consistent system. It has exactly one solution. The second thing that can happen is you can have parallel lines. So here's your x, here's your y. Let me just use a different color this time and pretend that I draw absolutely beautifully and that everything lines up. There's one graph. Here's another graph. They're parallel. They are never going to intersect. Since they never intersect, they have no solution, and this is called inconsistent. Consistent. And the third possibility is that you get two different equations, and when you graph them, you discover they're really the same line. They've just been disguised somehow, and we'll see how that works at some later time. If I graphed the lines, they would just be one atop the other, and that is called dependent. There are infinitely many solutions. They intersect everywhere is another way of thinking about it. Not the best, but there are infinitely many solutions. But it will work if you can think, since they lay one atop the other, they share every point. That might be a better way of remembering. Every point is a solution. Okay? Now, the other thing to emphasize is that for the consistent set, you basically saw a graphical solution. You graph them, you read the coordinates where the lines cross. For the consistent case, unless those points are very neat and tidy, a graphical solution is not very practical. So I'm going to write graphical as only practical. Graphical solution is only practical for neat cases, neat little integers. So I'll just remind you, consistent, inconsistent, and dependent are three new vocabulary words for you. You'll need to be able to recognize those. And that will be the end of this segment.